Hi guys, today let us talk about search algorithms. I recently learned about these two types and I want to share this with you guys. Anyway, the first type is the linear search algorithm. So how this works is like this. We have an array from 0 to, let's say, until the index of 8, or rather the length of 8. So our array has the length of 8. So we can have items like 1, 2, 3, 4, 5, 6, 7, 8, like that. And linear search works by doing something like walking through each of the index, or through each iteration is what they call it. So for example, we want to find the value of 6 in this array. So to find this value of 6 inside the array, or to check whether it exists or not, then we will go through this array one by one. To do that, we can check the first index, which is the very first item in the array. So ask this, hey, for this index, are you equal to the value? If yes, then we return this index, or just return true, or whatever we want to do if this value that we're currently in is equal to the value we want to find. However, if it is not, then we will move on to the next iteration. So move on to the next, and now we will ask the next item on the array is if it is equal to the value we are looking for. And it will go on and so forth until we find the value that we are looking for or not. And if not, then we will just return null or whatever we want to return. Okay. Now the big O notation for this, so big O notation stands for pretty much how much time it will take for this to process. And this is how they try to measure up algorithms. So it's called big O notation. Now usually based on what I learned, you should drop the constants and only look for the things that you will do repetitively. So for example, in this case, we will repetitively walk through each of this. And in the worst case scenario, it will take us, so if we do this one by one, and the worst case scenario is that we do not find the value we are looking for, so that means we actually walked through the overall, or rather through all items in the array. So that means we would have walked through this array equal to how many items the array has. So that would be the length of the array. So that means the big O notation for this is O of n. And n stands for how many, or like how much item is there inside of the array that we are actually looking through, or looping through in this case. Because the implementation for this in coding is a for loop, or a loop, or in general. So to loop through the array, for example, an array of 0 to 8, we will say for let I, or the index, equal 0, and as long as the index is less than the length of the array, then we will just move on to the next index of the array, or the next iteration. Okay, there we go. I hope this looks understandable. We will move on to a code editor after this anyway, but yeah. Okay. Anyway, so we will loop through each of this. So this is the equivalent of walking through each item in the array. So as long as the index we are in is less than the length, so the length here, this is because to access an index or an item of an array, the first item is actually equal to array, and then the brackets, and inside of that would be the index we pass on. And to access the first item, we would pass on 0, then so on and so forth. Okay, so we would have an if condition inside of this for loop based on what we did earlier. So we will ask each item, hey item, are you equal to the value we are looking for? And to translate that in code, we will do if the current item we are in, so just the array, and to access an item in an array is to provide, okay, is to add brackets beside it, and then the index of the item, so I, the current item we are in, is equals to I, or the index, and we will check if it's equal, so a comparison or equality symbol, which is either 2 equal signs or 3 equal signs. So 2 equal signs in JavaScript, okay? So 3 equal signs exist, I think, only in JavaScript. This means that we will check for its type equality as well. So this is not relevant to the algorithm, but I will just tell you what it is. So this 3 equal sign is a strict no, com comparison operator, which will check also for the validity of the types of two items. So for example, we have a string of 0, let's say, and we have a number of 0. So this equals sign here, or comparison operator, will say that 0, or the string of 0, is not equal to the number 0. That's because a string is not equal to a number. But if we only had two equal sign in here, then this will return true, because the string of 0 is still 0 in value, and the number 0 is still 0 in value. Okay, anyway, let's move on to the algorithm. So if the current item we are in is equals to the value we are looking for, then we just want to return true, or whatever we want to do. So either return the item or the index of the item. And then after going through all of the items, then we want to do something. We want to tell the thing that accessed this search algorithm or functionality that this item that we are looking for does not exist within the array that we just looped through. So at the end of the for loop down below, we want to return, so either whatever kind of message we want, or in this case, we can just return false or null. This is my first time to use a whiteboard in Canva, so I guess this is not bad. But anyway, this is the overall implementation of the linear search algorithm. And linear search is pretty much self-explanatory, which is that it will search an array linearly, one by one. So let's move on to the code implementation. Okay, so say that we have an array of cons array of 1 to 8, just like earlier. So 1, 2, 3, 4. Yeah, let's have that autocomplete for us until the 8. So now the length of this array would be 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So the length of the array is 8. So now let's actually translate our code from earlier to the code editor. So we have a function, because we want to do this again and again, I guess. So this function will be called linear search. And this will take in two parameters, and that would be the array that we want to look into or to search into, and the value that we want to get from the array that we are going to look into or search in. And inside of this, we will have just a for loop. So we will walk through the array that was provided to us. So to do that, we'll say let I equal 0. There we go. We have autocomplete. Oh, okay, there we go. And as long as the index is less than the array that length, because once again, to access an item inside of an array, we actually subtract everything by 1. So to access the first item, we will have array 0. And to access the second item, we will have array 2, or inside of the bracket notation, of course. All right. So now we will just have an if condition here to see if the current item that we are in is equals to the value that we are looking for. So we will have if array, and to access the item again, bracket notation, index, there we go, is equals to the value we want to search for. Then we will just return, so let's say we want to return the index, so return I. But if it does not exist, after looping through all of the items in the array, then we will just return null, or that means that this value does not exist. So let's try to const index of 6, and we'll say linear search, the array, and the value would be 6 as well. And we just have a typo here, should be small h. There we go. And we want to console log the index of 6. And now to check if this is true as well, we'll just have another console log below. If index of 6 is equals to, again, to access the index of an array we have from 0, first item, so we'll just count. So 0, 1, 2, 3, 4, 5. Okay, so is the index of 6 equals to 5? Let's check it out. Let's run this code. So node search algorithm. Let's press enter and see the result. There we go. Congratulations, we have implemented our first search algorithm. Now there's a better algorithm for this, and that is called the binary search algorithm. That's because the worst case scenario for this algorithm is that it will run equal to the array, to the length of the array. So for example, we have a billion items, so that means if the item does not exist, we will loop through each of them a billion times, something like that. But anyway, let's move on to the next algorithm. Okay, let's go to binary search. Now let's have an array once again. So an array from 0. Oh, what's this? Why is it like this? Oopsies. We don't want that. Maybe like this big. Okay. So from what happened? There we go. An array from 0 to 8 once again. And for binary search, we do this differently. Binary search, what it does without the implementation that I learned is that, for example, we will take in 10% of the array and check if the value that we landed on, for example, this value here, are you equal to the value we want to look for? Then if not, it will go through again 10%, or rather, if the value that is in here is actually less than the current value, or let me repeat myself. For example, we jump 10%, and at the 10% of this array, the item that we are in is actually less than the value we want to search for, then that means we will move to the right, because this means that the value we are looking for is on the right side of this current item we are in. So again, jump by 10%, and for example, on this next iteration, the value that we are in, or the item that we are in, is actually less than the value we are looking for. Then we would be looping, or rather we would be going back to the previous iteration of 10%, and then now looping linearly between the previous value that we had, which was less than the value we are looking for, and the next value that we had, which was greater than the value we are looking for. So that would mean this would be equal to a linear search, because we would then be looking for this one by one. Oh, I apologize. I actually turned off the noise cancellation earlier. Oops. Oh well. Anyway, let's move on. So to actually solve this 10% by 10% problem, then what if we actually just do it half by half? So this is what I learned again earlier. So to do that, for example, half by half, we want to take the half of this array, so example 0 to 8. So the half of that, the length, so half of the length, which is 8, that would be 4. So we would be 1, 2, 3, 5, 6, 7. So 1, 2, 3, 4. We would be here at 4. So now we will check, is this item, which is on the 4, so 1, 2, 3, 4, yeah, on this index, we're in half of the length, is this item equal to the value we are looking for? Then that means we just return. It says that. But then we will check, if this value is not equal to the value we are looking for, then is it less than the value we're looking for? Then if yes, we will actually divide this current midpoint by half once again. So now to do that, that means that our previous highest point will now be equals to this midpoint. And then this, and then again, what we do to the highest point is to divide it by 2. So 4 divided by 2 is 2. We will now go here, which is 2. So now we'll check, is this value equal to the value we are looking for? If not, if yes, then return it. If not, then check, is it greater than the value we are looking for, or is it less than? If this is less than, if this item is less than the value we are looking for, then that means we we want to look to on the right side. To do that, we just say, we just increase the current midpoint that we are in, half, right? Is it half? No, right. Yeah. So basically, we will divide the midpoint by 2 once again, and then increase it by that amount. So 2 divided by 2 is equals to 1, and then 2 plus 1 is equals to 3. So now we would be on this point, and then by that point, if it's not equal, then we just return null, and most probably it will be equal to the value we're looking for, so we will return this index. Okay, so the key takeaway here is that in binary search, we will check the midpoint every time. So in the midpoint of 0 to 8, the midpoint is 4. And if this item here at the 4th index is less than the value we are looking for, that means the value that we are looking for, so value we are looking for, is actually on the left side of this array, or of this midpoint right here. But if the value we are looking for is greater than the value of the midpoint, then that means the value we are looking for is greater than, or rather on the right side of the array, or of the midpoint. So that is the key takeaway for binary search. Now I cannot explain fully well about the big O notation of binary search, but from what I learned, it's equal to O of log n. That's because we are always dividing the length of the array that we are looping through or the items that we are going through. Because if you remember, 0 to 8, get the midpoint, which is 4. And then if it's not equal, divide it by half again. So for example, it's less than, so we have 2. And then again, 1 until we reach it. So 8, so we have 1, 2, 3. Is that it? Yeah, somewhat like this. So much shorter than linear search. All right. Whew. All right. Why don't we try moving on to the code? So for example, we want to declare, so binary search, and we want to loop through the array of 0 to 8. And in this function, we have 3 things to take care of. First, the midpoint. So how can we get the midpoint? Well, that would be by dividing the highest point by 2. And what would be the highest point on the first iteration? Well, that would be the length of the array. So we can say that let higher highest point, or high, because I cannot really write something that long, is equals to array dot length. Okay, let me check this. And then for the low, we just want it to be equal to, on the first iteration, low, to 0. That's because in order for us to get the full length, or half of the length of the array on the first iteration, we have to make this equal to 0. Because I will let you see the formula down here. So the formula for this would be, so we have the low plus, then first get the difference between the high and the low. So that would be from this point to this point right here. But of course, yeah, from this point, the highest point, to this lowest point, let's get the difference between them. And the difference would be 8. And that would be the highest point, which is the array that length, 8. So now we divide it by 2 to get to 4 right here. So now 0 plus parenthesis, substitute this rather. So we have 8 minus 0 divided by 2. This would be equal to 4. Now there's one more thing to note in this formula. We need to also get its lower integer value with math.floor. Now what math.floor does is round down the value of a decimal, well, round down the value of a decimal every time. So if we have 4.6, this will be equal to 4. If we have 4.8, this will be equal to 4. If we have 4.3, this will be equal to 4. So this is what math.floor does, is that it will round down a decimal to its nearest integer value or whole number value, no matter what. Okay, so now we have the formula, and let me just write this in a better way. Okay, so we have floor, or round down, value we get from low plus, get the difference between high and low first, because divide we will always get the length between whatever we are iterating through, and then divide the length by 2 after that. Then of course we will add the current low we are at, and then get the rounded down value of the sum. Now, based on what we tackled earlier, if the high is actually, so if high, oh, no, not high, if the midpoint, okay, so this is equal to midpoint, midpoint, there we go. So if midpoint or if the value of the midpoint, so our midpoint is greater than. So that means, for example, we have the array here, 0 to 8. If the value or if the item in this fourth index, so for midpoint here, is greater than the value we are looking for, so that means the item here is greater than the value we are looking for, so that means the value we are looking for is less than the item in the fourth index or the midpoint. So that means this 4 right here will now be our new highest point because we actually want to take half of this, or rather go to the point which is half of the current midpoint. So that would be 2 right here. To do that, we just do high equals to midpoint, like that. Now on the next iteration, excuse me, on the next iteration of our loop, we will also do this formula once again. And of course, this initialization is actually outside the loop. So like this is, there we go. This is in its own block, let's say, its own square rectangle block. Okay. We will have high equal to 4. So now we can do the formula again, substitute. So 0 plus 4 minus 0 divided by 2. So 4 divided by 2 is 2. We have the midpoint is now 2. Okay. Let me just delete these numbers. Excuse me. So now we did that problem. We solved the problem of wherein we actually want to take to go to the half point of the midpoint when the value or when the current item that we are in is actually greater than the value we are looking for. In here, we solved it. And of course, don't forget like the return condition if the please wait. If the item that we are in is equal to the value, then we just return. Okay. Now we have one more problem, and that is if, for example, the item on the second index is actually less than the value we are looking for, so that means the value we are looking for is greater than the item we are currently in, which is the second index. So that would be the third index in this case. We need to go to this third index in this example up here. How can we do that? Well, we can just say we want to, so if the current item we are in from this midpoint is less than the value we are looking for, then we just want to declare the lowest point. So this lowest point, or rather this lowest point of 0, so take note that we are at this point, right? At 2, and the lowest point is 0. Oh wait, no. Rather, take note that our highest point is 4 and our lowest point is 0. There we go, my bad. Lowest point is 0 and our midpoint is 2. We just want to increase our lowest point, which is 0, equal to the current midpoint, which is 2, plus 1. So that would be 2 plus 1, 3. So now our midpoint would be 3, and then our highest point would now be 4 on the next iteration. So let's test this out. So now on the next iteration, we'll do the formula once again. We have low, which is now 3, plus, so the highest point is 4, minus 3, divided by 2. And now to solve this, we would have 3, or rather 4 minus 3 is 1 over 2, 1 half, that's 0.5. 3 plus 0.5 is 3.5. Of course, round that down, that would be equal to 3. And now this 3 would be the third index. So check. Is it equal? If it's not, then we will do one more thing. So for example, if it's still greater than, then we will declare the highest point equal to the midpoint, which is 3. But then it will get to complications and we don't want that. So we actually want to stop this to the point wherein if the lowest point, since it is called the lowest point, if the lowest point if low is less than high, then that is the only time we will do this searching. If it is not anymore and we still didn't find the value, then we will just return null, just like in the linear search algorithm. Wow, my first ever whiteboard. Goodness me. Anyway, that's somewhat the gist of it. So let's try moving this to code. So first, let us actually declare the function of binary search. Then we will take on the array and the value that we want to find. So value to find. All right. So based on our implementation, we actually want to declare the lowest point first. And the lowest point will always be equal to 0 or the first item of the array. So let lowest point equals to 0 index and highest point on the first iteration will always be equal to the length of the array. So from 0 to 8, for example. And then now, our condition earlier was actually to search through the array while or if the lowest point is always less than the highest point. So to do that, we can just say while, or we can also do the statements do, and then while, but in this case, I want to do it in this way. So while the condition lowest point is less than highest point, because we will actually change the highest point as well, we can do this for loop. Okay. Oh, I mistyped the highest here. Okay. Oh. And to actually find the midpoint, we had our formula earlier. For that, we have const midpoint is equals to math.floor to always round down the value that we get. So that will be equals to lowest point, loss. And then first subtract the length or the highest point value to the lowest point to actually get the range that we want to look through. So that would be highest point minus lowest point over 2, then just divide it by 2. All right, and now of course the value would be value oh, to check equals to the array. To access that, we just say midpoint, the midpoint of the array, like that. So just to check for a condition on whether to return or to stop this loop, if we found the value, so we'll ask, hey, the current value we are in, are you equal to the value we want to find? Then I want you to do something. Either, of course, we want to stop the function, so just return. Or if you want, you can break the overall while loop or stop the loop and go through the next stuff that you want to do in the function right here. But anyway, in this case, we just want to return the index of the midpoint. Okay, and now we have another condition, which is to check if the midpoint is less than, oh, rather, my bad, if the value to check is less than the value to find. Value to find, not check. There we go. So for example, our value to check is 4 and our value to find is 6 from the array of 1, 2, 3, 4, 5, 6. That means our value to find is on the right side of this value to check. And so to change that out, we just want to increase our midpoint. And to do that, we just say lowest point is now equal to the current midpoint plus 1. And if the value to check is actually greater than the value to find, so that means, for example, our value to find is 6, and the current value that we are in is this realistic? Like, but anyway, for example, our value to find, let's change it up to 3, and our value to check is 4. So that means our value to find is on the left side. So we just change the midpoint to, or the highest point to the midpoint. And I think that's it. Let's try this out. First, we actually want to return null if we cannot find it. There we go. We have const index of 6 binary search equals to binary search the array from earlier and the value of 6. We have console.log index of 6 binary search. Let us try to run this to node search algorithm. Oh, we had a problem. What was the problem here? Ah, I made a typo. Should be midpoint at M. There we go. So we have node search algorithm. There we go. So from this array, the index of 6 is 5. So 1, 0, 1, 2, 3, 4, 5. There we go. We got it correct. But if, say, we want to find 1, let's just try it out. Again, node search, search algorithm. There we go. We got 0 because the start of the array, which is 0, that's where we can find the value 1. Let's try something that does not exist, which is 11. So node search algorithm, we get no. And to actually check for this, for the performance of this um algorithm, we can do something like const time. Okay, I'm not sure. I forgot how to do this, but let's try it. Performance now. And then at this point, if in here or down here, we can say const time and equals to performance dot now, and then we can console dot log time taken will be um time minus time. And let's try it out. CLS node search algorithm. Oh, there's a problem. Performance. Oh, actually, of course, it's just a typo error right here. There we go. CLS node search algorithm. There we go. Wow, that was very fast. Or did I do it the wrong way? Well, I'm not sure. Probably the other way around. Yeah, I think it's the other way around actually. Amen, minus time. That's the other way around. Okay. Node search algorithm. Yeah, there we go. That's very fast. But if we try to do it on this side, let's see if it's better or not. Const time and is equals to performance that now console log time and minus time. You can say this is the linear search. There we go. And let's just declare the time here. Const time equals to performance dot now. Okay, and let's try to call this linear search function below. So we'll have const index of 11 linear search equals to linear search array 11. Then we'll have 11 here, and here as well. Okay, try to console. Let's just try to run this actually and see the difference. Node search algorithm. Oh wow, would you look at that? The linear search took 11 milliseconds, while the binary search took less than a millisecond. Goodness. Anyway, whew, that was fun. And disclaimer, I actually just recently learned about this, and this was a way to make me really remember how it works, especially for binary search, because the linear search, I've been doing this a lot of times, but the binary search is pretty new to me. However, I do understand much of the concept, and I just needed to take a solid grasp of it. But yeah, I hope you learned something, and thank you for going along with me, and good luck on your development journey. Goodbye and learn well.